Hello, in this video I'm going to show you how to create a polyphonic algorithmic synthesizer using Max MSP. The algorithm is going to come from what is called the Collatz Conjecture. This is one of the most famous unsolved problems in mathematics. We are going to implement this conjecture into an algorithm, we are going to derive a lot of notes, harmonics, and numbers from this algorithm, and then we are going to pack all of it into a polyphonic synthesizer and generate some nice music. Let's get to it. Alright, so what we want to do is to understand the Collatz conjecture, implement it or a version of it in Max MSP, and then see which kind of sounds we get from it, and then finally make some music with it. So the first step depends on our understanding of the Collatz conjecture. So I have the Wikipedia page open here, and as always I will just note that this is a very in-depth topic, right? If you really want to understand the mathematics of the Collatz conjecture and why it's a conjecture and how it has been tried to be proven, there is a lot of information here. However, I'm just interested in this very first paragraph and this little box here, which is going to give us all the relevant information to make some cool sounds come through this conjecture. And here it says that the Collatz conjecture is one of the most famous unsolved problems in mathematics. In this video, unfortunately, I will not be solving this conjecture. If you do, more power to you, you'll be very rich and probably very, very successful. However, I'm just going to examine it right now. Right, and it says that this conjecture asks whether repeating two simple arithmetic operations will eventually transform every positive integer to 1. So put in simpler terms. The idea is this, right? And I'm going to look at this box here now. If I take a number, any positive number, anything that's larger than 0, and then if I check if it's even or odd, and then if I divide it by 2 if it's even, and if I instead multiply it by 3 and add 1 if it's odd, and if I keep doing this over and over again, am I going to get 1 as a result? Right? Because as we are going to see, if we try to do this experimentally, as in if we just take a bunch of numbers and plug it through this system, we are going to get 1. And the unsolved problems part comes in when we try to prove that any positive integer is going to end up at 1. So what we have to do is then to apply this simple algorithm in Max, right? We want to take a number, we want to see if it's even or odd, we want to divide it by 2 if it's even, we want to multiply it by 3 and add 1 if it's odd, and then do it again, and again, and again, and again, either until infinity, or until my computer runs out of battery, or until we have some kind of exit condition that stops this whole process. So let's go back into Max and let's actually write down the steps, right? So take a number, take a positive number, check if it is even or odd. If it is even, it was divide by 2? Yeah, it was divide by 2, right? Divide the number by 2. Let's write it like this. If it is odd, multiply the number by 3 and add 1. Repeat until ... As I've said, we'll see what happens at that point. Now, the main object I want to use is called int, which is short for integer, and the point of this object is to store an integer value. This is like a container. It's a bit close to the idea of a variable if you have experience with text-based programming languages. Right, why am I doing this? Because I want to repeat this task over and over and over again. And to be able to do this in an effective way, I need to take the result of the previous iteration, load it somewhere, which is going to be this int here, and then send it out again when it's time to iterate once again through this algorithm. Now, int can accept an argument, it can be its initial value, or you can set an initial value by using a number box and the second inlet, right? So this is not going to trigger any output, but it's going to internally change what is contained in int. And then if I send a bang to the first inlet of int, it is going to send out whatever number is contained inside, right? Right now it's 42. If I put in my favorite number, 55, when I send the bang, I'm going to get 55 and so on. So this can be one way of implementing this, right? I can think of this right inlet as a starting point, positive integer. This is going to be my starting point. And then the left inlet, the bang, is going to be start the process. And let's put a few exclamation marks so that we know we are excited about this. All right, now what do I have to do? I have to check if this number is even or odd, right? And this is one of the classic basic programming questions. How do you figure out if a number is even or odd? And I believe the simplest way to do this is to use what is called the modulo operator, or the modulo object. So an object that has this percentage sign as the name. And what it does is that it's going to divide the incoming number by whatever the argument is, and I'm going to make the argument 2, and it is going to output the remainder, right? As in, if I constantly subtract 2 from this number, am I going to be left with a number that cannot be divided into 2? We are, of course, thinking in terms of integers. There are no float numbers in this video so far. Right, and what is going to happen is, well, if I put in 55, I can, like subtract 2 again and again and again and again and again, but essentially at the end I'm going to end up with the number 1, which cannot be subtracted by 2, so it is going to give me 1. And this is all a very flowery, nerdy way of saying if I put an even number into this process, I'm going to get 0. If I'm going to put an odd number in this process, I'm going to get 1. And once I have those 1s and 0s, I can direct the process into whatever I want. Right, let's just write it down just to be sure. So if even, we are going to get 0. If odd, we are going to get 1. That is the idea. Right, okay, then secondly, we want to do either a certain operation on the number if it's even, or another operation if it is odd. And there are a few ways we can handle these, like if-then statements, right? There is in fact an if object in Max we can use. I'm not going to use it though. I'm not a big fan of the if object in Max MSP. What I will instead do is I'm going to create a gate. I'll create the gate object, which is going to take an input and it's going to send it from a given number of outlets, well, one of a given number of outlets, right? So if I give the gate object the argument 2, I will have 2 outlets, right? So I will have 2 possible roads that the input can take. It will not be both of these at once, it will be one or the other. Now the left inlet of gate is going to open one of the gates, right? And we can see this in action by, let's see, just sending an integer number into the left inlet, right? So I believe if I send this left inlet the message 0 and hover my mouse over the outlets, yep, gate output 1 is currently closed, gate output 2 is currently closed. If I send it 1, I will get gate output 1 currently open, gate output 2 currently closed. If I send it 2, then gate output 1 is currently closed and gate output 2 is currently open. Now, what am I trying to do with all this? Well, I'm trying to get the result of my modulo operation, right? And use this as a basis for selecting which one of these gates are exclusively going to be open so that my initial number can go through either from the left outlet or from the right outlet. Right, now I know that I want to send gate, let's see, either 1 or 2. And it's a bit of a problem, right? Because here I'm going to get 0 or 1 when I figure if the number is even or odd. And here I want not 0 or 1, but I want 1 or 2. And I can use my very advanced mathematics knowledge to just add 1 to the result of my even or odd operation. And now I'm going to get if even 1, and if odd 2, right? So if the incoming number is even, it's going to open the first gate. If the incoming number is odd, it's instead going to open the second gate, which means now I can define the process, what's going to happen to the even and odd numbers in these 2 separate tracks. And I can say, okay, if it's even, I want to divide the number by 2, right? So new object, division 2. There we go. Okay, and if it is odd, I want to instead multiply the number by 3, right? So asterisk with the argument 3, and then I want to add 1. Okay, and I'm going to get whatever the result is, and I'm going to route these for now to the same number box, right? And keep in mind, we are not going to get overlapping messages because it's always going to be either or. a number is either even or odd, meaning either one of these gates might be open at a moment, but not both of them exclusively, meaning we are going to get either this output or that output that will be visualized here. All right, so it looks good so far, but there's actually this little hidden problem that is going to mess things up when we try it. So let's try it. Let's input my favorite starting point, 55. Let's press bank, and we are going to get 166. Good. What if I press this again? I didn't get anything. I wonder why. If I press this again, I didn't get anything again. And it's kind of stuck. I'm just clicking this button over and over again, and this is stuck. Now, why is this? Well, the problem lies within the order of the messages, right? Because it's a very basic Max thing. Remember, Max always goes from right to left, right? So when there's any kind of data flow, first the right-hand side of things are evaluated, and then the left-hand sides of things are evaluated. So I think there is a cool way of visualizing this that is new and exclusive to Max 9. Let me just reset my gate objects to make sure everything is as it should be. So this new option is illustration mode. If you go to debug in your Max tab, and then if you choose illustration mode, something cool is going to happen when you input values. For example, if I input 55 and press enter, I can actually see the value go to the right inlet of the int object. This is really useful when you are trying to figure out the signal flow and see if there are problems caused by the signal flow. So let's first think about what we want to happen, what we want the algorithm to do, and then let's see what actually happens. What I want to do is to first check if the number is even or odd, and then based on that route the information to one of these two processes. Simple enough. And what is going to happen if I press this back? It's going to go here, but now it is just sending the number to the gate, and then it is sending the number to our is this even or odd system. And if you have keen eyes, you probably have noticed that that's the other way around, right? It's not supposed to be like that. First, we have to see even or odd so that once we send the number to the gate, it knows where to go. Otherwise, it's just going to be stuck after a certain amount of points, because first we are going to send it to a gate that's closed, and then we are going to close the gates, if that makes sense. So the solution to our problems is to use an object called trigger, or T if you're one of the cool kids that work with Max MSP. Both of those are the exact same thing. And I'm going to type I and I, two separate arguments, I as the arguments. And this essentially means this. When there is an integer number coming into this trigger object, first, send the integer coming into this object from the right outlet, the rightmost outlet, remember, right to left, and then send again whatever integer is coming in from the left outlet, right? Using this, we can make sure that the order of operations are very, very, very specific in our process, right? So this is what that is not what I'm going to do. This is what I'm going to do, is that I'm going to cross the streams a bit to make sure that things are fine. So now when I send this number, let's try it. We set our starting point, and when I start the process, boom, it's first sent here. We are seeing if it's even or odd. Okay, that opens the right gate, and now the number is being sent through the appropriate gate, so it's being processed, and we are getting 166. All right. Now if I do this again, the exact same thing is going to happen, right? 55 is going to go through here, it's going to open the right gate, and then the information is going to go through here. So we have figured out the Collatz conjecture. At least we figured out one step of the Collatz conjecture, because we are missing this. We are missing the repeat part, right? I have to repeat this over and over again to see what happens to my number. So I want to take this 166 and run it through the process again. And here's how I'm going to do it. I'm just going to take the output of the number box at the very end and plug that into the right inlet of it. So now, once we have the result of the previous step, it's going to load into int. It's going to be the new starting point, and then I can start the process again, and it's going to then take 166 as the starting point. So let's see. All right, well, we don't really need to do this again, actually, but let's just see things happen. Okay, if checks if it's even or odd, sends the number, processes it, and now 166 is going to go all the way to the second inlet of it. Okay, now I'm going to turn off illustration mode and I'm going to press the button again, and now I have 83 and 250 and 125 and 376, and I can click this again and again and again, and each time the previous number, the previous result is going to be put through the blender that is the Collatz Conjecture. By the way, notice that these numbers are getting very high. I expected it to converge to 1 or arrive at 1 after this many banks, but it's at 9,000, 1,000, 61, 184. But I have faith that if I click this enough, I am going to get 1, right? And once I arrive at 1, once I reach 1, what's going to happen is that it's going to go to 4, 2, 1, 4, 2, 1, 4, 2, 1. It's going to be this endless loop. All right, great. Now, what else do we have to do here to make this make sense to us? Let's think about it. So we have our Collatz conjecture. This is going to repeat over and over again. And in fact, I can use something like the metro object to just make this happen automatically instead of me having to click a button a million times, right? So let's set the argument of metro to 100 so that we get a bank every 100 milliseconds, and let's use a toggle to start and stop this metro. There we go. And now I can do something like this. I can again input my starting point, I can toggle this on, and now the system is happening automatically without me having to do anything. Now when I have this, right, when I know that it's going to go on indefinitely, I do want an exit condition. I do want something automatic that is going to stop this toggle. It's going to turn it off once the result is 1. So that is our next step, to automatically, or to have an exit condition to stop this loop from happening, so we can, we don't hear 142, 142, 142 over and over again when we eventually sonify this information. And a simple way of doing this is to use the cell object, which is going to output a bank if the input matches the argument, and make the argument 1. So now, if the input is 1, right, and we can do this, toggle the metro on. Maybe it's a bit fast, but each time we have a 1 here, this button is lighting up. The cell object is sending out a bank. And if it's sending out a bank, then what I can simply do is to take that bank, and look at this, we are going to do another closed loop here. I can take this bank and put it into toggle, because when toggle receives a bank, it is going to either turn itself on or off. If it's on, it will be off. If it's off, it will be on. Right, and well, this is it. This is the Collatz conjecture in Max MSP. Let's do it one more time just for fun before we move on. Okay, 55 starting point, toggle is on. We're going through all these numbers, calculation is being done until we arrive at, drum roll, we arrive at 1. And then we stop. It's over. It is done. So now the question is, well, how do we make this make sound, right? And this question is the heart of algorithmic music. And this is what we are doing. We are taking an algorithm and we are trying to make sounds and hopefully music from those sounds. And this is actually the part in which we can be very, very, very creative, right? So essentially, we want to take this number and make it mean something in a musical context. And in theory, this could mean anything, right? I can type in musical parameters and then say, well, this could be pitch. Right, it could be intervals, it could be chords, it could be the velocity or the loudness of a note, it can be the timbre, it can be rhythmic patterns, it can be musical phrases, it can be large-scale form. Right, maybe you can compose a piece that's based on the progression of the Collatz conjecture when your favorite number is given as a starting point. I don't know. I mean, I feel like I can just type in 20, 30 more things before I'm actually genuinely bored and I have to find other musical parameters. Now in this video, I'm just going to try to match things to pitch, maybe also to velocity, but the rest I'm going to either leave it as an example for you, the dear viewer, or I'm going to make videos on those some other time. So how are we going to turn this into pitch? Well, a very naive and a basic, but still valuable approach could be to take these notes as MIDI notes, right? Because we already have integer numbers representing musical data in our digital world. I can always create a case slider. I can create a make note object and give it a velocity and duration like 120 and let's say 500 milliseconds. And I can always take the result of this and route it to note out. There we go. I can always send this to note out. There, and what is actually happening is that I'm getting numbers, integer numbers from K-slider, which is then interpreted as a MIDI note that goes from 0 to 127, if I remember it correctly. So let's try this. Let's take the output of our conjecture, and then plug it into this number box, kind of overriding whatever would come out of here, and then let's just play that note. Let's see, 55, and here we go. Okay, sounds more like a typewriter than actual musical notes. And I think the problem is the fact that the ending was nice, the landing was perfectly fine, but I think the problem is that, well, we're getting a lot of numbers that are above 127, right? I mean, you remember me noting that, I mean, this stuff goes up to like 9,000 and can go even higher, depending on whatever happens. We have to assume that this conjecture has the potential of going to like infinity. Right, so if you're okay with this, well, here we have sonified the Collatz conjecture, but I think we can make this a bit nicer. And what I can do is, again, to use the modulo object, right? This time not to figure out if the incoming number is even or odd, but to make the incoming number wrap around a range of values. What do I mean by this? If I type in 128 as my argument to the modulo object, I am going to wrap whatever value is coming from my resulting number around 128. As in, if it's 0, it's 0. If it's 1, it's 1. If it's 127, it's 127. If it's 128, we loop back to 0. And then if it's 129, we keep counting from 1, 2, 3, 4 until we reach another 128, in which we loop back again to 0. So this is going to ensure that no matter which integer number we have, it's always going to be between 0 and 127, and the increase in numbers will still end up as a closed loop, as a loop between 0 and 127. And maybe instead of my convoluted explanation, I can simply run this again with the modulo on. Okay, that was much better. It still sounds a bit random. I think we can have other approaches. We can create other approaches that work a bit better with this logic. But before that, maybe I can also deal with this metro right here, right? Because I can also make the timing of the metro difference. I can use an integer number box into the second inlet of metro and set it to something slower, like 250, right? So 4 times a second, I'm going to hear a note. And then we are going to have a more subtle melodic line. And I can change this in real time too if I want to. Well, when it's really fast, it's actually really cool. Let's try to make it as fast as possible. Okay, so every millisecond we are going to hear a note. Nice. Beautiful. Okay, now this is one way we can deal with this, right? It can work as MIDI notes, sounds nice, sounds a bit random, which depending on your musical goal, it might not be exactly the thing you want. But another way we can think about this is to take the integer number, or starting point and all the successive iterations, not as MIDI notes, but as frequencies. Right? And then we can convert that frequency into a MIDI number, and then we can hear the result. And I can tell already by what happens to the number that the result is going to be very harmonic, right? But let's try to implement it first. So I am going to treat whatever comes out of here, and I don't need to loop it around 128 anymore. I am going to treat whatever comes out of here as a frequency. But my MIDI system does not take frequency information, it requires MIDI notes, and therefore I'm going to use F to M, frequency to MIDI, frequency to a MIDI note number, right? So when I have my Collatz number, it gets transposed into a MIDI note, and before we hear it, let's just see which numbers come out of it. And then if the numbers are fine, they are going to be played through our MIDI engine. So let's again take 55 as a starting point. Let's set the metro back to 100 and let's start the process. As you can see, we are not hearing anything, that's fine. And notice that the numbers are actually very reasonable, and that's because a frequency of like 10,000 is still somewhere in our keyboard. The only thing to watch out for is the ends. A frequency of 1 is apparently the MIDI note minus 36. I did not know that's the first time I find about this. But this means that we might want to make sure we clip the numbers to a range, right? I want to clip the numbers between 0 and 127. So if the incoming number is less than 0, it just becomes 0. And if it's higher than 127, it just becomes 127. Knowing that, let's try it again just to make sure we have the right results. So here the numbers are doing their own thing. They're going through the blender. And now we are going to have, and there it is, 1, but it's less than 0, so we're going to get 0. All right, and now let's do it one more time and let's actually hear the results, and let's enjoy the harmonicity of what's happening. Beautiful. It's really cool. Yeah, I think this is a bit more cool, right? It's a bit more harmonic, definitely. It's like this cool arpeggiator. And if you have sharp ears, or if you have ears that have experienced a lot of musical intervals, you maybe notice we are either jumping up or down octaves, or we are going up or down a fifth, and those are the only things. And that may be why it sounds so harmonic, because we are really doing these very basic integer jumps. We're either going up a perfect fifth or going down a perfect fifth or going up or down an octave or a combination of those two kinds of intervals. And why is this happening? I mean, it's not really important to know why that is happening, but there is a reason why that's happening, and that has to do with our possibilities, right? Because I'm either dividing the frequency by 2 or I'm multiplying it by 3 and I'm adding 1. And I will immediately say that, well, adding 1 to a frequency, 1 hertz to a frequency, well, it's not going to do much. We're still going to hear the same thing, right? However, if we multiply a frequency by an integer number, we are going to get overtones, right? We are going to get the harmonic series. We're going to get the overtone series. The first, the octave, then the fifth, then the octave again, then the fourth, and so on and so on. And what happens is when we multiply the frequency by 3, we are actually getting the third harmonic, meaning we are getting an octave plus perfect fifth. And then we are adding 1, but like I said, that doesn't do anything interesting. And when we divide the frequency by 2, we are actually just going down an octave. We are halving the frequency by an octave. And these two are the only possibilities. So what happens is then that we simply hear bunch of harmonic relationships, perfect fifths and octaves, and this will hold true for any kind of starting point we are going to have. There, or 200 maybe? Or about 453 as a starting point. There. So maybe this is a bit more cool. Definitely it's a bit more pleasing to my not always musical ears. All right, now that's really cool, and I think we can take a final step and we can evolve this into a synthesizer. Right, what I mean by this is that I want to have polyphony. I want to have polyphonic, algorithmic music. And maybe that's what I'm going to call this video, actually. That's a very cool term, polyphonic algorithmic music. And I essentially want to be able to input multiple starting points and to be able to hear multiple notes, and I want to have each voice have its own instance of the Collatz Conjecture running. And to be able to do this well, I have to use an object called polytilde. And I have been dreading this day. I don't think I've made any videos on polytilde because it's a complicated object. It's an object I have not mastered completely myself, and it's a very in-depth topic, right? So I want to be very practical with how this object works. And what this object essentially does is that it manages polyphony / DSP for patchers. We are not going to be doing any DSP. We are not working with signals in this video, we are just working with messages, but still, it is going to manage that for us. It's going to solve the problem I just described, to have multiple voices with each running this algorithm as an independent instance. All right, now how Poly works is as such. We are going to create another MaxMSP patch. We are going to save it in the same folder as this main patch. And then this new patch will contain the algorithm that we want each voice to run an instance of. And we are then going to load that into Poly. Okay, so let's create a new patch. Let's keep it empty for now and let's call it, saving it into the same folder as our main patch, let's call it Collatz Poly.maxpat. Collatz Poly.maxpat. All right, now what I will do is I'll take my entire algorithm, right? Just take it all, copy it, and paste it into my Collatz Poly patch. All right, now I can save this Collatz Poly. I can go back to my main patch. I can actually delete all of this now. I only have Poly in my patch now. My main patch has Poly tilde, and I will give it the argument Collatz Poly. I will also give it a second argument, not polyp, but Poly. I'll give it a second argument, which tells Poly how many instances to have, what is the maximum amount of voices I want in the system, and I will just type in 100 because it's a nice number. Right, so now if I lock this patch and double click on Poly, I will see instead, instead of the separate patch, I am going to see an instance of the Poly patch in this new window, right? So I can confirm that I have loaded Collatz Poly into Poly by doing this. Now, that being said, well, this isn't a one-man operation, right? This Collatz Poly needs some inputs. This Collatz Poly needs to send out some outputs. And I essentially want to have a case slider. I want to input the starting points as notes, right? And I want to receive the output as MIDI notes, as whatever I would send to note out. All right, so let's start with the easy part. How do we do the output? Well, I'm going to go into my Collatz Poly patch, and instead of using note out, I will create the objects out with the argument 1 and out with the argument 2. Right? This will make sure that my main Poly patch, my main Poly object is going to have 2 outlets, and the right one is going to send out the velocity. The left one is going to send out the pitch. Let me save this patch. Let me go back to Poly. While the patch is unlocked, double click, right arrow, space, enter, and it's loaded yet again. Now there are 3 outlets. The rightmost one is like this extra joker outlet we don't really need, but now we have the velocity and the note name. Or the MIDI note number, more specifically. All right, cool. And what about the input? When I send a MIDI note here, what is going to happen? Well, let's do it like this. I'm going to go back into Poly, and I am going to create, I'm going to go back into my Poly patch, and I'm going to create a very specific object. Let's see if I can remember this off the top of my head. Poly MIDI in. Beautiful. Poly MIDI in. Now, this is a specific object that will send out information when the Poly object receives a MIDI note, right? Or a MIDI information, a MIDI event, more specifically. We can look at the help patch to see that, let's see, inside the Poly object of the help patch, we have Poly MIDI in and then MIDI parse, right? So that is also something we need. After Poly MIDI in, I need MIDI parse to make sense of this MIDI event message my Poly object is going to receive. And this object's a bit intimidating, but look at the first outlet. The note on and note off. This is all we need. It's going to have the note number and it's going to have the velocity. And we only need the note number, so I can unpack 0, 0. I can separate this list into 2 numbers, and the first one is going to be the note name. Right, and that can be my starting point, except I might run into a little error here, right? Because the number that's coming in is a MIDI value, but I'm treating my starting point as a frequency. So I should make sure to convert the MIDI information to a frequency before I send it into my starting point. Okay, that's nice. Now, secondly, I should start the process once we have a new note, right? And I'm going to do this by using the trigger object yet again. Let's see, I'm going to do T1I. What does this mean? What does T1I mean? Well, T is trigger as we know, I is the integer number that will come out of here, and 1 is just 1, right? So I'm essentially telling this object when the integer number comes in, first send the integer number here, then send the message 1 to toggle, starting the process. Right, and then the toggle will turn off automatically once we have reached 1 in our Collatz algorithm. So this should be it, right? Well, we'll find out in a second once we test it. The last thing I need is to format the input to this poly tilde object. So let me save my Collatz poly again, go back to my main patch, and note that I cannot really just take kslider and slap its output into poly. I in fact need an object called MIDI formats, which is going to prepare data for MIDI messages, right? And I'm sending poly a MIDI message. I'm not sending it a single number or a list. I'm sending it a very specific message. So I need to pack the two outputs of kslider, the velocity and the notes. I need to send this into MIDI formats. And then I need to take the second outlet, the MIDI event message output, and plug that into poly. And if everything is right, this should work. So let me reload poly again. Let me cross my fingers in the physical world here, and let me input a note, and let's hear what happens. Fantastic. So can I do polyphony now? Amazing. There are two last things I'm going to do before this tutorial is over. The first, I'm going to add something with velocity. And second, I'm going to, let's say, future-proof this poly tilde patch. So let's quickly add some velocity capabilities to this. Now, what I want to do is to have a starting velocity and not put it through the Collatz algorithm, but instead to lower the velocity on each step, so my voice gets quieter and quieter and quieter on each iteration of the Collatz conjecture. So I will create a parallel int object, another integer container. By default, this can have 120. The default thing doesn't matter actually, because when we get the velocity of the input MIDI event, I will just plug that input velocity into the right inlet of int, right? Then I will make it so that Metro's output not only triggers my starting point integer, my Collatz Conjecture algorithm, but it also triggers the other int, the velocity int. So this is the velocity information, right? And finally, I will make sure that this integer is multiplied by 0.99 and that the result is plugged back and therefore forced to be an integer again into the second inlet of it, right? And we can actually see this in action so you understand what is happening precisely. So 120 comes out, times 99 when converted back to an int is something around 118. Okay, then 118 times that is 116, and 114, 112, 110, 108, 106, 104, and so on and so on. So we are just incremental, we're actually exponentially making our velocity less and less and less until it reaches the 0 point. Right, all right, well then I can take whatever velocity I have at that moment and plug it into the second inlet of make note, setting the velocity, overwriting this 120 and setting it to whatever this velocity is. Okay, so that should solve the velocity problem. Well, not a problem, but a velocity feature, solves the velocity feature. Now, all right, and how do I finally future-proof this poly patch? I do it by using the this poly tilde object. Now, my poly object has 100 voices, right? And technically, the incoming value can be allocated to any of those objects. However, I want the new information to be allocated to voices, instances of poly, where this stuff isn't happening. We haven't sent a starting point yet. So for these kinds of problems, there is this poly tilde object, which can be used to set the instance of the poly tilde patch to busy or free. If it's busy, well, then the incoming messages will not be routed there until it's free. And if it's free, the incoming messages might be routed to that specific voice, to that specific instance out of 100 instances we have in our poly patch. And to set it to busy or free, or busy or not so busy, we just have to send it 1 or 0. 1 makes it busy, 0 makes it not busy. And well, look at that. The toggle here is exactly that, right? If I turn it on, it should be busy. If it's off, it shouldn't be busy. And as you might know, toggle sends 1 if it's on and 0 if it's off, meaning that now we have future-proofed our poly tilde patch. So to make sure everything is as intended, let's do a final performance. Let's load our poly patch again. Let's make sure everything in it is correct. And let's try this. You hear how it's getting more and more quiet. Now this I call beautiful algorithmic music. Note that we only did 1 or maybe 2 of the musical parameters. So this is, as it is with all my videos, as a starting point, right? So how do you do intervals with this? How do you trigger chords? How do you trigger rhythmic patterns? How do you trigger other things I did not consider here? This is just the beginning of algorithmic musical creativity, which you can make use of. So I hope you have a lot of fun with this. I hope you experiment and create a lot of cool music with this, and thank you for watching.